Hello students, this is the lesson for Newton's third law of motion for the 2E notes. So again, here's my contact information. As always, remember you do get 3 attempts on every assignment. Today we are going over Newton's third law of motion, and your 2E notes are due today. We don't have class, but you are still required to do assignments even on days that we don't have class. We are officially on day 9 out of 45, which means that we are a fourth of the way through the quarter. So please remember that zeros for Star 360 are being entered today. If you don't do Star 360 by today, you will be placed in the max amount of required live sessions starting next week. The 1D lab report is past due. All of them have been graded. It's 60% of your grade, so remember that you can't pass the class without it. And remember, the recording does go over every step and answer, so please make sure you do it while watching the recording. We have been talking about Unit 2, Newton's 3 laws of motions. We've already covered the first and second law. Today we're digging into the third law. So today we should be able to explain Newton's third law of motion in relation to interacting objects, provide examples of actions and reactions, and continue to explore Newton's 3 laws of motion. Again, we will do the 2E notes, which you should hopefully get 100% on because, again, all the answers are included in this lesson. So we're going to take a look at Newton's third law, talk about balloon rockets and how those are related. We'll do some calculations with Newton's third law, summarize the laws of motion, and then review our objectives and reflect. So at this point, we need to make sure your notes are open. So if they aren't already, you need to go to the Content tab at the top of your course page, your physical science course page. Click Unit 2, Forces in Motion from the menu on the left. Scroll down and click the 2E notes. And then once you've clicked on that, go ahead and click Start Quiz. Again, you don't need to do anything with it until I give you the answers. The answers are being provided word for word throughout this lesson. So Newton's third law of motion states that for each force there is an equal and opposite force. So every force does have an opposing force. It's probably something that you've heard in everyday life, but in physics this is something that we can definitely experience in everyday life. So in a rolling chair, if you're sitting in a rolling chair and you push forwards on your desk, you'll notice that it causes your chair to actually move backwards. So that's showing that there's an opposite force that's actually pushing you the opposite direction. Same thing with when you jump off of a boat, right? If you are on a boat and you jump off to the left of the boat this way, all right, it will actually push the boat to move to the right, which is why it's always really funny when people jump off boats because they don't actually get very far because the boat actually slides out from under them going the opposite direction. And if an astronaut in space were to throw an object upwards, the astronaut would actually begin to drift downwards. So let's say that our astronaut is throwing a rock and the rock goes up, then that actually has an opposite force that pushes him back down. Okay, so for every action there is an equal reaction opposite to the direction of the force. So this is Newton's third law. And keep in mind that these forces come in equal pairs, meaning they're exactly the same force. One's going in one direction, the other one's going in the opposite direction. And when we say opposite, we mean the parallel opposite direction, right? So if something is going to the left, the parallel opposite force would go to the right. If something's going up, the parallel opposite force would be going down. If something's coming forwards, the parallel opposite force would be going backwards. Okay, so that is Newton's third law of motion in summary. We can see the boat example here. So at this point, you should be able to do number 1 in your notes. Go ahead, try it out on your own, pause the video, and then play, and we will confirm whether or not your answers were correct. All right, perfect. So at this point, a person pushes forwards in a rolling chair. So our person is pushing forwards. And so what happens is the rolling chair actually moves backwards, right? So the opposite parallel direction would be backwards. So here we go. The object would move backwards, the object being the chair. When a person jumps left off of a boat, again, the opposite parallel force would be to the right. So in this case, the object moves to the right. So the person went left and the boat went to the right. And then last but not least, an astronaut throws a rock upwards. So the rock goes upwards, and that means that the person actually does the opposite direction, which the opposite of going up is going to be going down. That would be the opposite parallel direction of that force. So the person will begin to move down. Again, this is number 1 in your notes. Make sure you have that saved and that it is correct, and then we are going to move on. Okay, so let's go ahead and talk about an example with a balloon. So keep in mind that without air resistance and gravity, like in space, an object in space experiences every action and reaction in a very clear way. Since there's nothing to stop you from seeing every action and reaction in outer space, it's really, really obvious. Now, the problem is that on Earth, we do have things that are subtly kind of affecting how our world works. So we do have air resistance, we do have gravity, we do have friction. So for example, when we push on something, we don't always experience the opposite reaction of being pushed back by that object because there's friction that's actually keeping us on the ground, and friction is an extra factor that changes our experience. But in outer space, we would really experience every action reaction in a very obvious way. Now, since we can't do this in outer space, I'm going to go ahead and show you though a good example with a balloon, because a balloon does kind of demonstrate this pretty well because there's not as much friction in this example. So let me go ahead and show this to you up.
Third law of motion, which says every action has an equal and opposite reaction. It's the principle that sends rockets to the moon. If you want to try this at home, this is what you need. When I release my fingers, air pushes out of the balloon. That's our action. Our reaction is that the balloon moves with the same force in the opposite direction.
Okay, so what that is showing is very similar to how rockets actually work. So rockets usually actually have fuel, and that fuel goes out one way direction, and what happens is the rocket is able to then go in the opposite direction. So in this case, the air for our balloon goes out to the left, and the parallel opposite force is to the right, and so that is why the balloon begins to move to the right. So again, this is a very obvious example of action-reaction because there's very little friction and air resistance that are getting in the way of this. Again, much like a rocket in outer space. So this is number 2 in your notes. Go ahead, take a few moments, pause the video, and fill in the blank with the word space and only the word space, and then go ahead and continue playing. Okay, so here's the thing. If force is the same, right, equal and opposite, so equal forces, then why don't both objects always have the same motion, right? So for example, when a child jumps off of a big boat, the child seems like they move a lot, whereas the big boat doesn't seem like it moves as much, which seems strange if we're supposed to have equal and opposite forces. So here's the thing. Let's go ahead and actually do a little bit of math here to prove this to ourselves. So in this case, we have a small 32 kilogram child, which I'm going to annotate this. 32 kilograms. Kilograms tells me that this is a mass of our child. And they jump off to the right. The right is going to be the positive direction, off of a big boat with an acceleration of 4 meters per second squared. So the child has this acceleration. So I want to specify that the child's acceleration is 4 meters per second squared. So meters per second squared, again, this is an acceleration. Okay. Now the big boat, on the other hand, is 256 kilograms. Again, kilograms being a mass. In this case, it's the mass of the boat. So mass of the boat. And so in this case, we're going to figure out what's happening to the motion of the big boat, even though these objects still are supposed to have the same equal and opposite forces. Okay, so equal and opposite forces tells me that the force on the child, the force from the child is equal to the opposite or negative force of the boat. Okay, so this is Newton's third law in a mathematical form. So F of the child equals negative F of the boat. Now remember, force, the actual equation for force equals M times A, mass times acceleration. So you can actually plug in MA for both of these F's, for both of these forces. All right, so instead of saying force of the child, I can actually plug this in and create mass of the child times acceleration of the child. And on the other side equals negative mass of the boat and acceleration of the boat times acceleration of the boat. Again, just plugging in the actual equations for force. Okay, so here's the equation that we're going to use today. So first off, we need to plug in the mass of the child. So taking a look up here, the mass of our child is going to be 32 kilograms. I'm going to plug in 32 right here. Okay. And the acceleration of the child, we said the child jumped off with an acceleration of 4 meters per second squared. So I'm going to plug in 4 right here based on what I annotated in my problem. On the other side, again, we're trying to figure out what's happening with the motion or acceleration of the boat. So we're going to leave that as the variable. But we do know the mass of the boat, and the mass of the boat was 256 kilograms. So I'm going to plug in 256 kilograms. And remember to keep that negative sign, right? We do have a negative sign still showing that this is an opposite force. Okay, so now let's go ahead and solve this. So first we need to figure out, on the left side, we can actually simplify this. So 32 times 4 is something that we can easily do already. So I'm going to go ahead and open up my calculator, and that's going to be 32 times 4, which equals 128. So over here, I'm going to say that 32 times 4 equals 128 on the left side of my equal sign. And on the right side, I'm going to keep the 256, the negative 256. Because we're not ready to get rid of that yet. Okay, so here's the thing. We can see that we're multiplying negative 256 times the acceleration of the boat. So in order to get rid of something that's next to the variable that I want, the acceleration of the boat, I need to do the inverse to whatever's next to it. And inverse means opposite. So the inverse of multiplying by negative 256 is actually going to be dividing by negative 256. So I'm going to actually go over here and divide by negative 256. And on the left side, I'm also going to do the same thing, because remember, whatever you do to one side, you actually also need to do to the other side. So on the other side, I'm also going, of my equal sign, I'm also going to divide by negative 256. Okay, so now what this means is on the right side where I did the inverse and I got rid, and I divided by this instead of multiplying, this actually gets rid of all of this. This all divides out and you no longer see it. Okay, so now we just have the A of the boat, the acceleration of the boat, which is what we see right here. And on the left side, we need to actually do this calculation. So 128 divided by negative 256. Now, it's really important that we start off with our first number, which is 128, and then divide by negative 256. So negative 256. And I'm going to go ahead and press equals. And for my answer is negative 0.5, or negative half of a meter per second squared. So negative 0.5. And again, the acceleration units are meters per second squared. Now, what does this negative actually mean? Remember that accelerations can have directions. So our child accelerated to the right with a positive 4 meters per second squared. So our boat, on the other hand, is accelerating in the opposite direction, the negative direction, which means the boat actually goes to the left. So when you answer number 3 in your notes, make sure you choose the one that says negative and to the left, 0.5 meters per second squared. But what does this all mean? So again, they experienced exactly equal forces, but the difference is with those equal forces, the small child had a really large acceleration, whereas the big boat had a very small acceleration, because the big boat is so much more massive that it can't do as much of an acceleration with the same amount of force as the child. So that is why when you jump off of something that is much, much larger than you, it doesn't necessarily look like it has the same motion, but it is still equal and opposite forces. Go ahead and answer number 3 in your notes and pause the video and then come back when you are ready. All right, so in summary, Newton's 3 laws are the foundation for understanding motion, and they are based on the interaction between force and inertia. All right, so remember that forces cause objects to accelerate, right? Forces are necessary to do an acceleration, and an acceleration is a change in motion, any change in motion. Inertia, on the other hand, is an object's resistance to changing in motion, right? A body at rest wants to stay at rest, just like you, when you are tired in the morning, you want to stay in bed. The same thing happens with objects, or an object in motion wants to stay in motion, right? So again, forces cause objects to change their motion. Inertia is an object wanting to not change its motion. So the interaction between these, like a tug of war, is how we get Newton's 3 laws. So by understanding how we can force things to change their motion versus how things don't want to change their motion, that is where we get Newton's 3 laws. All right, so the answer for number 4, fill in the blank with the word motion and only the word motion. Pause the video and then play when you are ready. All right, so at this point, we should be able to match up all of the laws that we've learned over the past 3 days. So go ahead, pause the video for a moment, try this out on your own, and then come back. We will confirm our answer and then make sure that number 5 is saved in our notes. All right, so let's go ahead and match these up together. So Newton's first law, remember Newton's first law is this idea of inertia. An object in motion will stay in motion. Object at rest will stay at rest. They will keep their same exact motion or lack of motion until they are acted upon by an external outside force. So again, this is this idea of inertia where things do not want to change whatever motion they're already in, whether that's they have a velocity, a speed, and direction, or if they're at rest. Newton's second law, remember that Newton's second law is our famous equation, F equals ma, so force equals mass times acceleration. Or remember that we were able to rearrange it, and you could also rearrange it and say acceleration equals force divided by mass. They are still the same exact equation, just kind of in a different way. And then Newton's third law that we just learned says that for every action there is an equal and opposite reaction that is parallel to the force. So remember, if an object goes to the right, the opposite force will go to the left. Object goes up, the opposite force will go down. All right, so this is number 5 in your notes. Go ahead, take a few moments to match those up, pause the video, and then play when you are ready to continue. All right, so at this point, we were able to explain Newton's third law of motion, talk about examples of action-reactions, and summarize Newton's 3 laws of motion. So at this point, you should go ahead and self-rate your understanding of today's objectives. Hopefully, you are in the pretty good or awesome area. If you feel like you're still in the very confused or still need some help area, make sure you contact me with the contact info I showed you at the beginning of the video for some extra help. And then don't forget to write down to yourself what's one thing that you learned or one thing that you reviewed today, so that you are continuously solidifying that knowledge in your brain. All right, thanks so much, everyone, and I will see you later.